Hey, everybody. Welcome to our live stream, Tales from Beyond the Geofence. And today I'm really excited. We're going to talk about data and data standardization and interoperability. And while maybe you think that those things might kind of put you to sleep or elicit that eye roll, the truth is that those things are fundamental for working with drones and are going to be essential for us as we build out our capabilities, especially when we think about working amongst different labs. This idea of interoperability is something that we've been chasing for a while, and it's hard to do. And I'm going to start with a really simple example. I'm going to pull up a little ruler here. It's a ruler that you might have be able to go out and measure something in the environment, maybe the height of a plant. And if you notice, this ruler actually has both inches and centimeters on it. And so if you were to be trying to compare measurements between labs, you want to make sure that you're using the same units, right? And maybe even you know being having some sort of standard approach to setting limits on what's the smallest portion of a unit that you might want to actually indicate what's your rounding error. And because rulers are really simple, it's easy for us to be able to communicate those things and make measurements that we can compare around the world. So maybe transpose this idea of a ruler with a drone and think about how complicated all of those things are when it comes to trying to make measurements that are comparable across different labs. And also think about all of the things that you have to collect and annotate and curate to be able to make sure that people can use those data um, as you go forwards, right? Because we want this data to be useful down the road as well. And so this idea of interoperability is really important. And so we need a lot of projects that are focused on that to be able to sort of push the field forward. And so today I'm excited because we have a couple of people here who are joining us from our lab that have been working really, really hard on these kinds of topics. And they're going to sort of step you through some of the things they've been thinking about and working on in conjunction with a bunch of different partners along the East Coast of the US here. And so if we can invite them in now, we'll have get both of them up here in our view. And we have Justin Ridge with us here. He's a research scientist in the Mars lab here at Duke University, and a lot of his work is focused on coastal ecology and conservation, and in particular, recently doing a lot of work that's focused on using drones to study and support management of coastal resources like oysters and seagrass and mangroves. And so he has a lot of experience thinking about how we use drones to do these kinds of things. And with him, we have Christiana Falvo, who is a geospatial analyst in the Mars lab. And she's kind of our Swiss Army knife here at the lab. She works on a lot of different projects and has a lot of experience with data management and has been working really hard on one specific project that's kind of focused on interoperability and how we can use drones across, different space and time sort of spectra, and do that efficiently in a way that actually makes sense, right? And so I'm really excited to be able to have them join us and talk a little bit about those projects, and hopefully help y'all learn a lot more about how to deal with data and how to do these kind of standardized approaches to projects. So I want to pass it on to them now.
Thanks, Dave.
Thank you for that.
Yeah. We were just going to start off with talking really briefly about how our work evolved into drones, because I was doing my PhD just down the road at UNC's Institute of Marine Sciences, focusing on like some of these coastal habitats and monitoring changes through time, like Dave was talking about oysters and marshes, and we actually started collaborating with Dave on a project out here looking at some of like the barrier island change, and that really evolved into me coming here for a postdoc and just trying to figure out how we can use drones as a management tool. And so I've been helping Dave kind of build up the coastal mapping part of the marine robotics and remote sensing lab here. And then Christiana has her own pathway that she's taken to here.
Yes. Well, awesome. Glad you're here, Justin. And thank you, Dave, for the intros. I'm excited to be here in general and talking today to kind of bridge this gap between data management space and the drone space, because my first job out of college was sort of niche. It was in USGS as a data archivist, essentially. So kind of like a librarian, but for the scientific data in that agency. And I got the job. My old Frisbee coach from college was the one who actually went up to me after I graduated and said, congrats on graduating. What do you say about writing some metadata for the USGS? I was like, well, sure, absolutely, but what is metadata? I had no idea. I was starting on a pretty clean slate in the data management space, but through that job experience, learned very quickly the value that documentation has in science for ultimately making a scientific study last through time. So we were meticulously documenting these old studies that, if there was no sort of description about the data set itself, scientists today couldn't, understand or reproduce it or share it around. So really the documentation aspect of data and sort of data management, which is sometimes forgotten about in, the kind of like cutting edge spaces, really adds so much power to science. And so I got that experience. I carried it through my master's at Duke. So I did Duke's environmental management degree and kept focusing on data science throughout that, but kind of added in some more environmental management applications. But now I find myself here at the Drone Lab, and this project was such a cool way to bring in the data management experience, because as we'll talk about, just kind of the inherent nature of what we were trying to do in this project lent itself to really needing good, thorough, detailed documentation, and just really taking care of the data from, when it was collected out in the field all the way through to the archiving stage. So we'll get into all the dirty details of that.
Yeah. Well, let's do it. So that was the sort of lead into having your background. How has been dealing with drone data, been different than other types of data, right? Like that's this whole process.
Yeah, right. So like I said, I've had my hands on lots of different types of data through, work and school and different things, but drone data is kind of its own beast. It has this processing pipeline, or what I'm going to call a drone data lifecycle going forward here, that is pretty extensive and pretty convoluted. So what I have laid out on the slide here that you all can see is this rough, or I guess the three main stages rather of this drone data lifecycle that we'll be talking about. And it really is illustrating the journey the data takes from acquisition, or, going out into the environment and capturing what's the reality of whatever environment you're in, taking it through processing, so wrangling whatever you need to from that raw data, and then finally onto the analysis stage, where that data becomes information that can be used for research, management, or lots of different things. So this data lifecycle we're going to keep kind of coming back to, and is hugely important in this project that we're going to talk about, but is just hugely important across the board in science. So to give you guys kind of a sense of what the drone data lifecycle looks like, right? So this journey that data takes specifically when it's coming from a drone, we'll start with the acquisition phase, which is the pilot on the left there, and we'll kind of bring up these images here to illustrate more so what's involved in each of these stages. And so at the acquisition phase, that's when you're out in the field. And as a pilot, you are responsible not only for operating the aircraft and taking sort of flight factors into consideration, but you're also a photographer. So, the the interplay between an aircraft carrying a camera and all the weather conditions around you, all this needs to be taken into account because, you know, the amount of clouds going by, the level of wind in the area, you know, how steadily the aircraft is moving over the area you're interested in, all of that is going to ultimately affect the images that you take, and the quality of those images translates to the quality of your data and the information you're going to get at the end of the process. So really crucial first stage there. And then the processing phase is sort of the black box of the drone data lifecycle. There are a variety of image processing softwares out there. We use Pix4D, but the image processing phase is what essentially takes all the little photos you get from your drone flight, takes those and kind of creates these products that you then use in your analysis. So roughly what the software is doing is, first on that little box on the left there, you have, you know, this grid pattern of images after flying the drone like a lawnmower over the whole area that you're interested in capturing. The software is stitching those images together. Then you get this reconstructed point cloud surface that's shown in the middle there. And that point cloud surface, you do some georeferencing, which is essentially, making the point cloud surface as accurate a representation of that environment as you can. And from that point cloud surface, these products, we call them. So the orthomosaic is just a bird's eye view image of the site. The digital elevation model, DEM, there is all the different elevations mapped out on the site. And then sometimes we use these multispectral indices, that red product shown at the bottom there. And that gives us information about vegetation and photosynthetic activity and things like that. But so this processing phase has a ton of nuance in it, and that's probably the most detailed part of the protocol, because it's really like following a recipe and all this little settings you toggle, and how you sort of account for, you know, the imagery that you have and the site that you're studying. You have to make different decisions within this image processing software that ultimately affects the quality of the products you end up with, that are then fed into your analysis. So the analysis is this final stage where you take, you know, these different products and you dig into them and you extrapolate the information that you're interested in learning about your site or whatever environment you're in. So this is just to kind of lay out a visual for everyone, because like I said, it's kind of a black box and there's a lot that goes into taking, you know, the reality we see in this project's case in a marsh or tidal wetland system to the information that we can, you know, take into the scientific community or the management space or wherever. A lot that goes into that process, and along every stage of this process is opportunity for variation to be introduced. So this is kind of what we're focusing on today, right? It's if, you know, someone were to, you know, read a recipe but skip step 2 and 7 and 13 or whatever, they're going to get, you know, even if they use the same ingredients, they're going to get a way different, you know, tasting cake or whatever, right? The output, the information, the results are going to be different if you know, there's variation introduced into the other stage of the process. So this monster document we've created and our team has helped created was the main way we tried to account for and kind of get out ahead of this variability that is introduced across the life cycle. So yeah, that was a mouthful, but
it was. But it's an extensive, like in building the protocol, right? There's so many steps along the way that you could check or uncheck a box, and you know you could dramatically change what your output could be. So
Totally. Yeah. Yeah. Guess we can move on now to introduce the project that is gonna kind of illustrate this concept to everyone.
Yeah. So we have been involved in a couple projects that have been focusing in on how we can incorporate drone systems into tidal wetland monitoring and understanding. Some of these projects are geared towards understanding like really in the weeds, like details about like what the limitations are with this life cycle that Christiana was talking about, different steps along that way. And some of them are geared, more towards broader aspects of that process. But this was a project. So what we were doing is we were working with the NEAR system. So the NEAR system is the National Estuarine Research Reserve System. And this is the NEAR system, or NERS, depending on where you're from. They are a network of research reserves that are all along the U.S. coast, and like that includes Great Lakes, and that includes Puerto Rico. And so we were working in the southeast here of the U.S. and in the Caribbean with Puerto Rico as one of the project partners. And so we had 6 reserves that were involved in this process. And so we were looking at, we had the North Carolina NEAR, and that was located at Masonboro Island. And then we had the Northland Litwinia Bay NEAR in South Carolina, the Ace Basin NEAR in South Carolina, Sapelo Island NEAR in Georgia, the GTM NEAR in Florida, and then Hobos Bay in Puerto Rico. And what I'm showing here is this is a big group of people that are working on this across all 6 reserves, and then different group like our Mars Lab group. And then we also had NOAA individuals that were involved in aspects of this project. And so you have a bunch of different groups that are all collecting data, all processing it and analyzing it independently. And so that was kind of the setup for this, was understanding how can we have these outputs be reproducible if we're independently going through this process. And so I've also identified here, there were a number of individuals within these teams that were particularly focused on the technical aspects of these projects. And so they were devoting a lot of time into getting into the details and building the protocol that we produced.
Yep.
And so the protocol was geared towards really that the imagery derived data, right? So from the acquisition, processing, and analysis side of things that Christiana was talking about, that was all encompassed in that. And then the projects were also including this comparison to ground derived data. So understanding how those products that can be generated, one part is, can we reproduce them? But then also there was the aspect of the projects that was, how do those correspond to data that are collected on the ground? And so where is that different measurements that are being used? How are they comparable? How could they be comparable, moving forward through time, and understanding that?
Yes. And like Justin said, I mean, the whole point of this project was, what's illustrated in this little schematic here, to compare the imagery derived data to the ground derived data, because the question we're asking in this project is, can drones be used to measure all these different aspects of the wetland that, humans on the ground have been measuring for years? Can drones do that? Can drones see the same things that people can see on the ground? So that's I mean, the stage that this is at right now. And so the first thing we have to do is compare, use a drone to measure the height of the canopy, like the person is doing in the left side, and look at those 2 measurements, drone and person derived, and say, how close are they? So that's really the main purpose of this, the main kind of output of this, was those comparisons, which is the first thing that lends itself to this need for really good quality data that, stems from the standardized documentation. Because if you don't have, if if you don't have everyone and like the wide, broad team of people that Justin showed on the last slide following the same recipe and ending up with the same, comparable results, you can't make this comparison in the first place. So that's the first aspect that really lent itself to needing to document really well and thoroughly. The second aspect, oh yeah, you have something at it.
Well, I was going to say that reminded me that like the measurements that that you're kind of illustrating here, right? You have like different like vegetation height, you have like percent cover, you have biomass included in that, you have ecotones, right? Those are all sort of things that we were looking at. Some of those are part of a long-term data set that these reserves are collecting manually, right?
Yeah.
It's part of the system-wide monitoring program. They SWAMP is what they call it. And so a big impetus for the project was understanding sort of, can drones be used to enhance that program, and what
Yes.
level of to what level that can happen. So
Yes,
anyway,
totally.
back to your
all about monitoring marshes for the health and the longevity, which we'll get back to for sure.
Yeah,
that's a good point to interject that in. But yeah, so the quality matters to be able to make these comparisons, right? But the other reason that the standardization and the documentation is so important is because of the inherent variability we had just by doing this project across 6 different reserves. And so you see this mosaic of mosaics here. These are just snapshots from the drones that flew over these 6 tidal wetlands sites on the coast. And, they're all wetland ecosystems in the Southeast, but you can see how different these systems are. And so variability in just the landscape that you are photographing and studying makes a difference in sort of how you have to go about some things. But within each reserve, we had, different teams of people, all with different levels of experience. So some people had used drones before, some people hadn't used drones before, and every team member had to be able to follow the protocol, right, and produce the same outputs. So that was a huge factor. Each team also had a different set of equipment they had access to. So we had, a variety of different aircrafts. Different people had different access to sensors. So we had different types of imagery coming out of it. Everything even down to the image processing software. That varied between sites sometimes. So it was a challenge, but a great success of the project to create this, I'm going to call it again, a monster document that really kind of covered all the bases, or as many as we could at least, to account for as much variability as we could across this very kind of diverse board.
Yeah, and you can see even like some of because we had different reserves, had different sensors that they were collecting. You can even pick that up in some of these images you see, because some reserves were only using like a multispectral sensor. They weren't using like a standard RGB. And so that, right, like that creates this inherent like difference in terms of the products that are generated and how we deal with that. So
totally. Yeah. But I guess at this point we have a few examples now from the project that will hopefully illustrate to everyone, how one instance sort of upstream or earlier in this data lifecycle can really have a noticeable effect when you get to the end result. So we have a few examples that, and I'll say too, to start, that each of these examples happen kind of throughout the protocol development process. So they each were really valuable sort of learning opportunities that we could say, oh, this was unclear. We need to make this more explicit, and so these were all kind of incorporated into the document that is out there now. So we'll start by, and this schematic is going to keep popping up. So this example illustrates how the ACE Basin site, so in their acquisition of their imagery, so, you know, in the flight photo taking stage, one little camera setting got, you know, switched or something, and that resulted in all their images being just a little bit blurry. And, you know, blurry images don't sound like that big a deal, but at the time when we got, you know, all the way down to the percent cover analysis, and we're comparing results from that analysis, ACE Basin popped out as an anomaly, and it was largely due to that acquisition. So before I zoom into those blurry images, you can see I have just a couple illustrations here to orient everyone to what the percent cover analysis is. So percent cover is simply you have a square quadrat down on the ground, like the scientist on the left side of the screen. And you know, you have a series of these quadrats, but you go up to each quadrat and it's a visual estimation of what percentage of that square is covered in vegetation, essentially. So we get a visual estimation on the ground. That's our ground-based estimate that we then compare to our drone-based estimate. And how we get the drone-based estimate is flying a drone over those same, you know, that same site with those same quadrats laid out. We then process the imagery, analyze it in ArcGIS, which is a geospatial software. And in ArcGIS, the software can classify the imagery based on what it can see in the photos, essentially, and quantify, you know, how much of the square is vegetated and how much of the square is not vegetated. So those are the two kind of approaches, you know, that we get percent cover estimations from. We then compare those. But like I said, ACE Basin, when we took the difference between the imagery-based percent cover and the ground-based percent cover, there was a big difference. So this is, you know, along the y-axis is kind of the magnitude of difference between those two measurements. And ACE Basin has a much greater difference compared to the rest of the sites. And like I said, the blurry imagery was a big contributor to that. So on the bottom left part of your screen, you see this sort of zoomed out view of ACE Basin site. You can see nice green, dense, tall form Spartina. So Spartina is like a nice marshy grass found in the lower parts of the marsh. You can see that from way far away, but in the middle of the site, this sort of grayish area, and I'll use my little pointer here. These grayish areas, it's not bare ground. It's actually the same type of plant, just in a kind of more sparse and less dense form. And so you can see the zoom in here on your upper right-hand side. You can see how blurry this imagery is. And this ultimately made it really hard for the software to distinguish between the Spartina and the ground. So you ended up with a classified version of that imagery that was mostly, you know, gray or unclassified and only little bits of green that it could see. And so that ultimately leads to this anomaly. Yeah, pretty big difference in the grand scheme of things, from a pretty small little, you know, probably just one little button on the camera before it took off. So yeah, it's kind of one illustration of that, you know, I don't know what to call it, like a cascade almost of one little difference at the beginning, cascading to a big effect at the end, and emphasizing that importance of, you know, that being very explicitly written in, like the camera settings being very explicitly written into the protocol.
Yeah. All right. So the next example we're going to talk about, it's not necessarily because of the equipment or some aspect of that, but it's more tied to just differences in the environment and how that might play out in imagery, and like understanding how that's affecting your final products. And so I'm talking about Hobos Bay for this part. And Hobos Bay, so in Puerto Rico, they their site that they are monitoring is actually, it's this mangrove site, and it's an area that was heavily impacted by Hurricane Maria a couple years ago, and so the mangroves in this area were like destroyed when Hurricane Maria came through. And so you can even see in this mosaic and a little bit in this image I have blown up from there that there's just so much dead material in there, but there's mangroves coming back. And so that's what they're really excited about, using drones to see this recovery of this site. But because a lot of the mangrove was removed, you have a lot of just open water, almost like in these. So this is inundated when they were collecting this imagery. And so you see in the image just a lot of water. And because of that, when you're processing through structure from motion, you have these open areas of water. It's just hard for that software to deal with that. And so you start getting that impacting your products. And so that's an example. So I'm showing here the surface model that was generated, and ignore the edges because the edges are all kind of like wonky from but what's happening is the center of this area where a lot of that open water and area is focused is creating a surface, an unlevel surface, that it's not just like a nice clean surface of water, that it's generating this weird kind of raised middle part. Yeah,
you're talking about this yellow area here is higher, right? Yeah. Yellow is higher values than these green low areas, but in reality it's all
flat, right? It's all just like one. Yeah. So this is just like part of what the environment looks like and how that plays out with this. And you can see this a little bit better when we look at what the software pumps out as the terrain model. So it like tries to remove as much vegetation and then like tries to give you what it considers a bare earth model. There's problems with this, but this gives you the idea of like where it's not a level surface right across that. So that's just part of understanding how the environment, can impact your products and your analysis, right? From that. And there are ways to mitigate this. And so there are ways that you could recover. This isn't like necessarily like, oh, we can't use this anymore. There are ways to get around this. And a good example is going to be something that Christiana talks about for the next example, for like how we can work around that issue.
Totally. But yeah, I love this example because it's kind of ties in, like you were saying, how the environment impacts the sort of process you have to go about. And I feel like operating in these different marsh environments was just a series of different lessons for us about how these different landscapes, I mean, the last site we showed, Ace Basin, all grassy and kind of like level, versus this one, those different landscapes make a huge difference in how you have to kind of handle processing and analyzing the imagery. And I feel like it's just a point of this effort in general too, is to learn about how to do this well in marsh ecosystems, right? Because it's drones are up and coming thing in research as it is, but marsh ecosystems are kind of this, I don't know, it seems less documented or reported. So to kind of like have these lessons and write down ways to navigate these challenges is a big success of the project, I think, too.
Yeah. And I will say, like, that talking about that, like, the Hobos was just it was such a unique site with this project because it was a mangrove site, right? Yeah. All the other sites were marsh, but this was like the mangrove side of tidal wetlands, right? So it was such a cool comparison with those other sites too.
Yeah, totally. So totally unique
with its own set of problems.
Yeah, totally, as they all had. All right, but so the last example we have here is highlighting like Justin said, it sort of brings in this idea of how to create an accurate surface of a marsh environment. And marsh environments in general are very flat environments. And that actually makes it pretty hard for the way the technology works and just sort of the process by which you can get an elevation model or sort of a map of the topography from just a bunch of photos from a drone. Much easier to do that in like a mountainous, variable topography system versus a very flat kind of uniform marsh system. So one way we improve the geo accuracy or like the location accuracy of our products is by using GCPs, and that stands for ground control points. And this one is an example of how, again, it was this instance of finding a spot in the protocol that was kind of, it could have been more explicit, and we made it more explicit because yeah, sort of how these ground control points were set out in the field influenced how the entire surface was reconstructed. And so I'll sort of bring up this image and explain it in a second, but first want to just explain that a ground control point is, if we just look at the left side for right now, this is a sparse point cloud surface of a marsh site, right? So like this is like a boardwalk going across. These are a bunch of trees, and then it goes down into a river here. So it's a big area, and a ground control point is one of these three little green dots that you see there. And it's essentially a point that you go out in the field before you fly your drone. You set these points down on the ground. You take the geospatial coordinates of those points so you know them. And then after you fly your drone over the area, you can see those ground control points, and then you can tell the software exactly where those points are. And that helps the software fix the whole rest of the surface and sort of, I don't know what the word is.
Supposed to.
Yeah, it's supposed to kind of, correct the rest of the surface to make it as geospatially accurate as possible. And so at first in the protocol, it said something like, make sure your GCPs are evenly distributed throughout the site, right? And yeah, use a minimum of 3. And so on the left side is kind of before and after. So the left side is, what went wrong, and then the right side is when we fixed it. But
I feel like it's gonna be more noticeable in the next slide.
yeah.
But you
it's
did
subtle now, but you can argue these are pretty evenly distributed points. Yeah, 3 GCPs in a nice little line, but
and to their, like, in their defense, right, their system, they really only access the marsh through this one boardwalk.
Sure,
And so
yes.
it's very difficult for them to like access other parts beyond that boardwalk. So this was like their best attempt to evenly distribute.
Yes, absolutely,
control.
absolutely. But it ended up that, these GCPs are basically in a line, which, by the way the software kind of fixes and adjusts all the rest of the surface based on those points, you can see in this next slide. So on the left is, the erroneous situation we're still talking about. You can see the whole surface is tilted. So the 3 GCPs are shown down the middle there. And, in reality, this marsh is not on a hill, but it looks like it's just a big old hill right there. But so how we had to correct for this was, rather than having just 3 spaced out in a line here, we had to create 2 more. And so this weird word here, I didn't know this word, quincunx or something.
Quincunx, yeah.
Quincunx. This is actually a word to describe how like the 5 dots on a dice are arranged. So they're not all 5 in a line, but they're evenly spaced out so that, the right side has a dot, the left side has a dot, everybody has a dot. And that helps the software kind of evenly correct the entire surface and create a much more accurate representation of the marsh surface here. So yeah, like Justin said, it was, in part just the nature of this site only having a boardwalk through this kind of inaccessible terrain. But it was also an opportunity for us to improve the protocol by not just, being more explicit and using this funny word is in the protocol now, but also kind of creating a workaround where you can sort of, in post-processing, you can create two GCPs sort of, artificially in a way, but knowing the elevations in those areas to help the whole surface be constructed in a way that's more accurate.
Yeah. So we could have, like in that situation, you could, if there were features, static features that you'd be able to go back to, right? You could survey those in and then add those into your processing to recover that. And what we ended up doing was we were using actually the water line, like features at the water line, because we knew the water line was an even surface across that area of the marsh. And so we were able to use those to correct the whole surface.
Yeah, that was a pretty clever approach, which, so this gets back to too, like the documentation of these best practices. How did you know that? Was that written down somewhere, or had you just kind of tried that sometime?
That was something that I had been able to use for other surveys that I'd conducted around oyster reefs, which are just all surrounded by water. And so being able to like pull those all onto the right plane, because as I showed with the hobos example, like just having so much water creates weird deviations from your in the 3D model. So that's using those waterline features, which is like the waterline uniform across at least the area that we'd be surveying in one flight, right? That we could use that as a point of reference. So
I see. Yeah, so you could measure the changing elevation of the oysters by knowing, having that set water level, flying at the same water level every time, kind of thing.
It kind of all put it back into the plane that it needs to be. So,
I see.
And I think that other people have used that too. So like there was a bit of figuring that out, but also that seems like there are other instances I've seen that being used. So
gotcha. But yeah, great to have that sort of thing written down.
And that's what I'm talking about, like our ability to, yes, maybe your situation has created a product that is off, but there are ways that if you know how to deal with them, you can correct for that. You can mitigate those issues. So
yeah, totally.
Because if you look at, and also if you were to look at the quality report coming out of something like what's on the left side here, where your 3 GCPs were very nicely fitting to their GPS coordinates and vertical datum, that it would show you that like it has a really low projection error, but obviously that's
because down the middle, that's pretty accurate. It's at about 0 meters, but it's not showing you, oh, well, this is like 5 meters and this is like -5 meters. It's kind of hidden in the quality report. So subtleties.
Yeah, totally. But having like all of that information, right? Like building up this protocol, creating this like extensive plan for like how to collect, how to process, how to analyze the data in a way that would be reproducible if somebody else, grabbed that same data set and went through the process. It's like super powerful and something that's like, yes, what we created was geared towards, this specific program within the NEAR system, but it's highly applicable, like beyond that, right?
Yeah, absolutely. For anyone trying to study or observe changes over time in a wetlands or tidal wetland system, any sort of application under that umbrella, this could be hugely helpful for that. And I mean, it was started to be talked about a little bit, I guess, as far as, all was said and done with the project pretty much, and kind of talking about, well, what happens now and like, how is this going to be used? And I mean, for a lot of these sites, like Justin said towards the beginning, the NEAR system is nationwide, and they're all these protected wetland sites that have been monitored for decades. I don't know how many decades, maybe a couple decades.
Good question.
I think, yeah, we'll have to phone a friend for that one. But
Yep.
in any case, I mean, the measurements that were taken, say, in the 90s, I mean, those wetlands are different now, and they're going to keep getting different. And so to be able to, A, use the most cutting edge tools that we have access to continue the monitoring, but B, making sure that the timeline stays connected, right? So it gets back to like the power of data management and documentation for science. It's that, you know, if we just have this little piece here, we don't know as much about the whole system. We need the whole timeline to be able to really get a handle on how these things are changing. And so to be able to meld, you know, the newer drone data with the older ground data potentially, or, you know, whatever ends up happening, more detail can only help, you know, future people look back on a study and say, okay, that's how they did that, or that's why this piece is weird, or whatever.
Yeah.
So
Yeah, and I'll also say that, you know, we weren't necessarily setting out to replace, right? Like, we weren't trying to say we'll develop this to replace those monitoring methods that they're using within the program, but at the same time, there is interest, right? They want to know if they can use this to augment, like basically broaden their reach with like those measurements, and also to reduce the amount that they're having to go into some of these habitats and potentially like impact them, because there are, you know, long-term marsh monitoring transects that create like actual kind of scars in the marsh. And so just trying to think of ways to make that process better for everyone, including the marsh.
yes, including the marsh.
Yeah. And I'll say that, you know, thinking about the documentation, like we created some pretty like elaborate metadata documents, right? That we had, you search for like metadata templates that we then were adapting, we were building on, right? For like all of this to be stored with it.
Yeah.
Right?
Yeah. That was an interesting process to kind of, because, and I mean, and Dave, you can feel free to jump in and kind of comment on this too, because this is starting to broaden out now into sort of how drones are an up and coming and, you know, just like ever growing tool for research. And as that grows, we're sort of, I feel like, at the point of talking a lot about and really trying to figure out what data management for drones looks like. And yeah, the metadata development for this project in particular, it's like, well, it's kind of, you're imagining somebody 10 years from now, 30 years from now, I don't know, in the future, coming back to your work and being like, well, how did they do this?
Yeah.
You know, or why does that image look like that? Or how is this product processed? Or why is this you know, so all these pieces, it's like, well, what do they need to know? And that's what we had to talk about and decide. And we, you know, ended up putting together a version of metadata, or this description of this data set. But I think, yeah, what that looks like, where those things are stored, who it is that's adding to these different repositories, all those things are really in the process of being figured out, it seems.
Yeah. Totally.
Yeah, thank you very much. It's a really compelling example. And it kind of shows how complex things can get, right? Started off with a really simple example of a ruler and showing really quickly that if you have a different kind of ruler, or if you're thinking about things in a different way, you can come up with really different measurements. And sometimes that's a setting in a software system or on a piece of equipment, but sometimes it's actually, some function of the environment that you're working in, and so there's a lot of stuff to try and coordinate. And so when we think about remote sensing in general, if we think about, say, Landsat, hugely important to our understanding of the planet. And every Landsat mission has, 15 scientists that are all working together to figure out exactly how to deal with the nuances of those data as they come down from orbit.
Mhm.
And what we really want is we want to have drones functioning like a constellation of low Earth orbiting satellites. But we don't have that sort of unique sensor. We have all these different parameters that we have to deal with. And what that really means is that we need collaboration, like what you're talking about, right? Where people are actually working with a diverse set of systems in diverse habitats to actually see, how much variation is generated and define those kinds of practices that will help minimize that and allow us to compare across things. So it's a great example of how to do that. And I'm hoping that we'll see more projects like that, because that's really going to help us, move things along.
Yeah.
I want to point out too that, in the description below, there's some links to the project information that will help people, kind of follow along and see how this is progressing. Um, and I think the other thing that's really nice is that as we progress, we're thinking about other ways to try and help. And one of the things that's coming online soon is the development of a community of practice here in the Southeast US, called Drones in the Coastal Zone, that will really help us, develop these kinds of comparative comparisons and collaborative projects to help get, over some of these hurdles that are really important for us to address.
Totally. Yeah. The more people talking about it and coordinating, the better, for sure.
Yeah.
Yeah, absolutely. So questions, it'd be nice to hear a little bit more about things. One of the things that I'm always kind of interested in is, what were the sort of, like, I don't know, hardest things to deal with. In some situations, some things are low-hanging fruit. You can address them really easily, but some things are real bugbears. And I wondered if you guys had, like, sort of examples of, maybe each of that end of that spectrum of problems when it comes to this interoperability issue.
Mm.
Do you want to talk about your deep dive into calibration target and how that plays out with?
Oh, gosh. Yeah.
That was just like we had, so a couple of the sites are using multispectral, like I mentioned, multispectral sensors. So they're sensors that are collecting reflectance across their sites, not using a standard RGB. And when you're using those, there are calibration targets that come with them in order for you to, when you fly, be able to create a baseline, right? That your data can be sort of take out some of the confounding of different lighting conditions and different aspects of that. So,
Mm.
but I feel like some of the tech team went really deep into understanding sort of how, when you're collecting flights across a time span, because some of these sites are pretty big, and so they're collecting flights over a changing solar angle, and how that plays out when you use different calibration targets taken at different times, and how some software allows you to do just one, some software allows you to do two. It just, like, it makes a big difference to your actual, like, products.
Mm.
Right? Like, you notice that there was some differences that played out there. I don't know how extensive, I can't remember how extensive they were.
Yeah, we started noticing or wondering, I'm not sure, I guess, at what point the question came about, but because, like Justin said, some softwares you can pick, you want to use the pre-flight calibration images or the post-flight calibration images, and sometimes the flight was like 20-30 minutes and the cloud cover, the lighting conditions had changed a lot, so it's sort of, you pick one or the other. And we wondered, well, if one analyst, and this was like the recipe test, and shout out to Brittany, because Brittany and I don't know how many times we processed this one site, but we started out with the same imagery, and we're using the same software, same steps, everything we did exactly the same, except for we switched which calibration images. So Brittany used the pre-flight, I used the post-flight, and we saw what difference that made in the NDVI value. So basically an index that describes sort of how the plants are reflecting light. And if you are calibrating all of your multispectral imagery to different like standard images, then your end result you could see in just the raster, we were trying to compare, well, across the whole site, there's slightly different range. Okay, that seems like maybe not such a big deal. But then when we got to the point of the analysis, and this is, again, we've been talking about this like this ripple effect, this cascade effect. When we got to the analysis point of comparing the biomass curves, Brittany and my curves looked pretty different. Like if you're looking at those two different pieces of information, you're going to draw very different conclusions about that site. So like that one subtle difference in the processing, made a pretty significant difference in the results. Yeah. So, I mean, the trials and tribulations of like getting down to that nitty gritty, I guess that's what I was thinking about when Dave asked that question of sort of the biggest challenge. And for me, as a technician who, I mean, the timing of this was funny because I joined the Mars lab kind of right after you guys had flown the drones and collected the imagery. So we had all this imagery and it was like time to process. And I had taken Dave's class in my master's, and so I had some experience with Pix4D, but I had no idea how deep it got. And so my experience was one of my main tasks for this job I was coming into was to write this protocol, but I had to like figure out, what was the best way to do it before I wrote it down, right? So just processing after processing after processing. But it's actually, I think, turned into a huge benefit for the protocol, because if I had 5 years of experience processing imagery, I probably would have taken a lot for granted and, not thought certain details were important. But because this was meant to be a document that, should be able to be, understood and used by a variety of skill sets, like beginners to advanced users, these questions that, these things that didn't work, like every day it was like something different was happening and I didn't know why. And you go online and you look through the Pix4D, like the software documentation, which is pretty good, but it doesn't get as deep as some of these things. And it's like the institutional knowledge. I mean, when I couldn't find the answer online, I'd go knock on Justin's door. And so then I'd work through the problem and then I'd write it down, like how we solve that problem. And that, I mean, we have a lot of institutional knowledge. I'm pointing at Justin because there's like a lot of like knowledge that you've gained from just the repetition and the experience of doing this type of work. I just wrote all that down.
Which I think, it was vastly beneficial to the protocol. And like, I would say, like, especially seeing like how well you can answer questions now that like are thrown at you from like team members that are struggling with some aspect. It's like you have leaps and bounds like this last year. So
yeah, struggling is learning.
Yeah.
So
That's right. If it was easy, we wouldn't be learning anything.
exactly.
Yeah. Wow. Well, that's great. Well, we're actually at about an hour now, so I think we'll probably end things here. I want to thank everyone for joining us. today as part of our live stream events, Tales from Beyond the Geofence. And I'm really thankful you tuned in and hope you found this useful. And I'm hoping that we'll see you back again sometime soon. We're going to try and keep on doing these relatively frequently, once every month or so. And so please, if you have any ideas about things that you would like to hear about that we might be able to shed some light on, drop us a comment in the in YouTube or send us an email, and maybe we can sort that out for y'all. But again, thanks everybody for joining. Thanks to Justin and Christiana for sharing their incredible journey through this process, and hopefully that's helpful for others that might be undertaking similar projects down the road. So thanks again, and as always, fly safe, and hope to see you soon.